Exploring the power of asynchronous streams in .NET 8. A deep dive into handling asynchronous data streams. Introduction to asynchronous streams in .NET 8. Asynchronous streams in .NET 8 provide a powerful and efficient way to handle asynchronous data streams in your applications. When working with large amounts of data or when needing to process data that is retrieved from remote services, asynchronous streams can greatly improve the performance and responsiveness of your application. Asynchronous streams are essentially a sequence of data elements that are retrieved asynchronously. They allow you to efficiently work with data as it becomes available, rather than waiting for the entire stream to be loaded before processing it. One of the key benefits of asynchronous streams in .NET 8 is their ability to handle potentially infinite data streams. This means that you can process data in real time as it arrives, without having to worry about the stream ever-ending. Using asynchronous streams in .NET 8 is straightforward. You simply declare and define an asynchronous stream, and then use asynchronous iteration to retrieve the data elements. Additionally, you can apply transformations and filters to further manipulate the data. This provides a flexible and efficient way to manipulate and process the data. Overall, asynchronous streams in .NET 8 provide a powerful solution for handling asynchronous data streams, enabling applications to efficiently process and respond to large amounts of data in real time. In the upcoming sections, we will delve deeper into the intricacies of asynchronous streams in .NET 8 and explore various techniques and best practices for handling and managing asynchronous data streams effectively. Benefits of using asynchronous streams in .NET 8. Asynchronous streams in .NET 8 offer a range of benefits that make them a valuable tool for handling asynchronous data streams in applications. Here are some key advantages of using asynchronous streams. Real-time processing. Asynchronous streams allow for the processing of data as it becomes available, eliminating the need to wait for the entire stream to be loaded. This enables applications to respond and act on data in real time, providing a more efficient and seamless user experience. Efficient memory usage. Asynchronous streams have the ability to handle potentially infinite data streams, making them suitable for processing large amounts of data without consuming excessive memory. This is particularly useful in scenarios where data is generated continuously, such as real-time sensor data or event handling. Improved responsiveness. By processing data asynchronously, applications can remain responsive even when dealing with long-running operations. Asynchronous streams make it possible to perform tasks in the background without blocking the main execution thread, ensuring that applications remain interactive and responsive to user inputs. Simplified code structure. Asynchronous streams provide a clean and organized way to work with asynchronous data. By using asynchronous iteration, developers can easily retrieve data elements, apply transformations, and implement filters, leading to more readable and maintainable code. Flexibility and scalability. Asynchronous streams offer flexibility in handling different types of data streams, and the ability to scale processing to handle varying workloads. This flexibility allows applications to adapt and efficiently process data streams of different sizes and speeds without sacrificing performance. Understanding asynchronous stream basics. Asynchronous streams in .NET 8 provide a powerful mechanism for handling asynchronous data streams in applications. To effectively utilize this feature, it is essential to understand the basics of asynchronous streams. At the core, an asynchronous stream is a sequence of data elements that are asynchronously produced and consumed. It represents a continuous and potentially infinite flow of data. To declare and define an asynchronous stream, the iasync enumerable interface is used. This interface provides the ability to iterate asynchronously over a collection of elements. In terms of implementation, asynchronous iteration and cancellation are key concepts to consider. Asynchronous iteration enables the retrieval of data elements one by one, as they become available, rather than waiting for the entire stream to load. This not only improves responsiveness but also enables real-time processing. Additionally, asynchronous streams support cancellation, allowing for the early termination of a stream operation if needed. Overall, understanding the basics of asynchronous streams is crucial for effectively working with these data structures. It enables developers to harness the power of real-time processing, efficient memory usage, and improved responsiveness in their applications. How to declare and define an asynchronous stream. To declare and define an asynchronous stream in .NET 8, developers utilize the iAsync enumerable interface. This interface allows for the asynchronous iteration over a collection of elements, enabling the efficient handling of asynchronous data streams. To declare an asynchronous stream, the iAsync enumerable interface is implemented by creating a method that returns an asynchronous stream. The method signature typically includes the async keyword and returns an iAsync enumerable object. For example, public async iAsync enumerable generate stream. For int I equals 0, I yield return I. Yield the current element in the stream. In the above example, the generate stream method creates an asynchronous stream of integers. It uses the yield return statement to return each element of the stream as it becomes available. To consume the asynchronous stream, developers can use asynchronous iteration using the await for each statement. This allows for the retrieval of elements from the stream one by one as they are produced. Overall, declaring and defining an asynchronous stream in .NET 8 involves implementing the iAsync enumerable interface and using the yield return statement to produce each element of the stream asynchronously. Implementing asynchronous iteration and cancellation. To fully harness the power of asynchronous streams in .NET 8, developers need to understand how to implement asynchronous iteration and cancellation. Asynchronous iteration allows for the retrieval of elements from the stream as they become available, enabling efficient processing of large datasets. On the other hand, cancellation ensures that the stream can be stopped gracefully when it's no longer needed. To implement asynchronous iteration, developers can use the await for each statement. This statement allows for the asynchronous retrieval of elements from the stream, one by one, without blocking the execution of other code. It ensures that each element is processed as soon as it's produced, maximizing efficiency. Additionally, asynchronous streams in .NET 8 support cancellation. Developers can utilize the familiar cancellation token mechanism for canceling asynchronous operations related to the stream. By passing a cancellation token to the asynchronous stream method, developers can gracefully stop the stream when desired, ensuring that no further elements are processed. Overall, implementing asynchronous iteration and cancellation in .NET 8 allows for efficient and controlled processing of asynchronous data streams. Developers can retrieve elements as they become available and cancel the stream when it's no longer needed, providing flexibility and responsiveness in handling asynchronous data. Managing asynchronous data streams with transformations. Transforming asynchronous data streams allows developers to manipulate the data, apply filters, and extract specific information, opening up a world of possibilities for data processing and analysis. In .NET 8, asynchronous streams can be easily transformed using LINQ operators, providing a powerful toolset for managing asynchronous data streams efficiently. By using LINQ operators with asynchronous streams, developers can perform operations such as filtering, projecting, sorting, and aggregating the stream's elements. This flexibility enables the extraction of relevant data and the reduction of unnecessary processing, improving overall performance. Filters and projections are commonly used transformations in asynchronous data streams. Developers can apply filters to the stream to retrieve only the elements that meet certain conditions, reducing the amount of data to be processed. Projections, on the other hand, allow for the modification of each element in the stream, enabling the extraction of specific properties or the transformation of data into a different format. Apart from LINQ operators, developers can also implement custom transformation methods to manipulate asynchronous streams according to specific requirements. These methods can be used to perform complex calculations or aggregate data from multiple streams. In summary, managing asynchronous data streams with transformations in .NET 8 gives developers the flexibility to manipulate and extract relevant information from the raw data efficiently. By leveraging LINQ operators and custom transformation methods, developers can streamline their data processing pipelines and unlock the true potential of asynchronous data streams. Using LINQ operators with asynchronous streams. Using LINQ operators with asynchronous streams is a powerful tool in .NET 8 for managing and transforming data efficiently. LINQ, Language Integrated Query, provides a set of operators that can be applied to asynchronous streams to perform various operations such as filtering, projecting, sorting, and aggregating elements. One of the advantages of using LINQ operators with asynchronous streams is the ability to filter the stream based on specific conditions. Developers can use operators like where to retrieve only the elements that meet certain criteria, reducing unnecessary processing. Projections are another useful transformation that can be applied to asynchronous streams using LINQ operators. Operators like select allow developers to manipulate each element in the stream, extracting specific properties or transforming the data into a different format. In addition to filtering and projecting, LINQ operators can also be used to sort the elements in the stream, order by, or perform aggregation operations, sum, average, etc., on the stream's values. By leveraging LINQ operators, developers can streamline and optimize their data processing pipelines, improving performance and extracting relevant information from asynchronous data streams. Applying filters and projections to asynchronous data. Applying filters and projections to asynchronous data is a powerful technique in .NET 8 that allows developers to efficiently extract and transform specific information from asynchronous streams. By using LINQ operators like where and select, developers can apply filters and projections to the stream, reducing the amount of data to process and extracting only the relevant information needed for further processing or analysis. The where operator enables developers to filter the elements of the asynchronous stream based on specific conditions. This allows for selective data retrieval, improving efficiency by discarding unnecessary data. For example, developers can filter a stream of sales orders to include only those with a certain amount or from a specific customer, minimizing the processing needed for irrelevant data. On the other hand, the select operator allows developers to transform or project the elements of the asynchronous stream into a different format or extract specific properties. This is particularly useful for extracting only the required information from a larger dataset, reducing memory usage and improving performance. By combining these operators with asynchronous streams, developers can streamline their data processing pipelines, extracting relevant information efficiently and improving the overall performance of their applications. It's important to consider the specific needs and requirements of the application to choose the appropriate filters and projections to apply to the asynchronous data. Error handling and fault tolerance in asynchronous streams. When working with asynchronous streams in .NET 8, it's important to consider error handling and fault tolerance. Asynchronous operations can encounter various exceptions and failures, so it's crucial to have strategies in place to handle them effectively. To handle exceptions from asynchronous stream operations, developers can use try-catch blocks to catch and handle specific exception types. This allows for graceful error handling and prevents the application from crashing. When an exception occurs, developers can log the exception details, notify the user, or implement specific recovery actions depending on the nature of the exception. In addition to exception handling, developers can also implement retry and fallback strategies to enhance fault tolerance in asynchronous streams. For example, if a network connection failure occurs while fetching data from an external API, developers can retry the operation a certain number of times with a delay between each attempt. If all Retries fail, a fallback mechanism can be implemented to provide alternative data or default values to ensure smooth functionality of the application even in exceptional situations. By implementing robust error handling and fault tolerance mechanisms, developers can ensure that their asynchronous stream operations are resilient and able to handle unforeseen errors and failures, providing a reliable and seamless user experience. Overall, error handling and fault tolerance are crucial aspects of working with asynchronous streams, and .NET 8 provides various tools and techniques to help developers handle these scenarios effectively and gracefully. Handling exceptions from asynchronous stream operations. When working with asynchronous streams in .NET 8, developers need to be prepared for potential exceptions that may occur during these operations. Exception handling is an essential part of ensuring the resilience and robustness of the application. To handle exceptions from asynchronous stream operations, developers can utilize try-catch blocks. By surrounding the code that may throw exceptions with a try block and defining specific catch blocks for the expected exception types, developers can gracefully handle and recover from errors that may arise. In the catch blocks, developers can log or display the exception details to aid in troubleshooting and diagnosing the issue. They can also implement custom error handling logic based on the specific exception type. This may involve notifying the user of the error, rolling back changes, or initiating recovery actions, depending on the nature of the application and the exception encountered. By proactively handling exceptions, developers can prevent the application from crashing or behaving unexpectedly in the face of errors during asynchronous stream operations. This ensures a smoother user experience and helps in identifying and resolving issues more efficiently. Implementing retry and fallback strategies. Retry and fallback strategies play a crucial role in ensuring the resilience and fault tolerance of asynchronous stream operations in .NET 8. These strategies provide a way to handle failures and recover from errors, minimizing the impact on the application's functionality. When implementing retry strategies, developers can define the number of retries and the delay between each attempt. This allows the application to automatically retry failed operations, improving the chances of success. For example, if a network request fails due to a temporary network glitch, the application can automatically retry the operation a few times before giving up. Fallback strategies can also be employed to handle failures by providing an alternative data source or method. If an asynchronous stream operation fails, the fallback strategy ensures that the application can still retrieve or generate the necessary data. This can involve switching to a backup data source, using cached data, or falling back to default values. It is important to carefully design and fine-tune these strategies based on the specific requirements and constraints of the application. By implementing effective retry and fallback strategies, developers can enhance the fault tolerance of their asynchronous stream operations, minimizing disruptions and providing a more resilient user experience. Evaluating and improving asynchronous stream performance. Fine-tuning the performance of asynchronous streams is crucial for achieving optimal efficiency and responsiveness in your applications. In this section, we will explore some key strategies and techniques for enhancing the performance of asynchronous data streams in .NET 8. When working with asynchronous streams in .NET 8, it is essential to evaluate and optimize their performance to ensure optimal efficiency and responsiveness. Profiling tools and performance metrics can provide valuable insights into the performance characteristics of your asynchronous stream operations. Once you have identified any bottlenecks or areas for improvement, there are several strategies you can employ to enhance the performance of your asynchronous streams. Firstly, it's important to evaluate the performance of your asynchronous stream operations using profiling tools and performance metrics. This will help you identify any bottlenecks or areas for improvement. Once you have a clear understanding of the performance characteristics, you can start implementing optimizations. One effective technique for improving performance is to utilize buffering. By buffering the data in memory, you can Reduce the number of expensive asynchronous operations required to retrieve or process the data. This can significantly improve the overall throughput of your application. Another approach is to leverage concurrent processing techniques. This involves dividing the workload into smaller tasks and executing them concurrently. This can be achieved using parallel programming constructs such as task, parallel library, TPL, or async, await pattern. Additionally, consider optimizing any external dependencies or resources that your asynchronous stream relies on. For example, you can fine-tune database queries, optimize network communications, or cache frequently accessed data to avoid unnecessary round trips. Remember to test and measure the impact of these optimizations to ensure they are indeed improving the performance of your asynchronous stream operations. Fine-tuning the performance of your asynchronous data streams will help deliver a smooth and efficient user experience while maximizing the potential of your application. Utilizing buffering and concurrent processing techniques. Utilizing buffering and concurrent processing techniques can greatly enhance the performance of asynchronous streams. In .NET 8, by strategically buffering the data in memory, you can reduce the number of asynchronous operations required to retrieve or process the data, resulting in improved throughput and responsiveness. Buffering involves temporarily storing the data in a buffer before processing it. This allows for batch processing, reducing the overhead of individual operations. By carefully tuning the buffer size, you can optimize the trade-off between memory usage and processing efficiency. Concurrent processing, on the other hand, involves dividing the workload into smaller tasks and executing them simultaneously. This can be achieved using parallel programming constructs such as the task parallel library, TPL, or the async, await pattern. By leveraging multiple threads or executing tasks concurrently, you can take advantage of the available system resources to speed up processing. However, it's important to carefully manage concurrent access to shared resources and handle potential synchronization issues. Proper synchronization techniques like locking, thread-safe collections, or using asynchronous primitives can ensure data integrity and prevent race conditions. By incorporating buffering and concurrent processing techniques into your asynchronous stream operations, you can significantly improve overall performance and maximize the efficiency of your application. Remember to consider the specific requirements and constraints of your use case to fine-tune these techniques for optimal performance. Real-world use cases and best practices. Real-world use cases. Asynchronous streams in .NET 8 have a wide range of applications in various real-world scenarios. Some common use cases include processing large datasets. Asynchronous streams are particularly useful when dealing with large volumes of data that would otherwise cause memory or performance issues. They allow you to efficiently process data in a streaming fashion without loading the entire dataset into memory at once. Real-time data ingestion. Asynchronous streams are well suited for real-time data ingestion scenarios, such as collecting and processing live data feeds or sensor data. They enable you to handle data streams in a responsive and efficient manner. Parallel processing. Asynchronous streams can be leveraged to achieve parallel processing of data. By distributing the workload across multiple threads or tasks, you can enhance performance and responsiveness, particularly when dealing with computationally intensive tasks or time-consuming operations. Resource-intensive operations. Asynchronous streams are ideal for handling resource-intensive operations such as file I/O, network requests, or database queries. With asynchronous streams, you can ensure that these operations do not block the execution of other tasks, resulting in more efficient resource utilization and overall system performance. Best practices. Here are some best practices to consider when working with asynchronous data streams in .NET 8. Optimize buffer size. Experiment with different buffer sizes to find the optimal trade-off between memory usage and processing efficiency. A larger buffer size can reduce the overhead of I/O operations, but it may also increase memory consumption. Use asynchronous primitives. Take advantage of asynchronous primitives like semaphore slim or async semaphore to control access to shared resources and manage concurrency in a safe and efficient manner. Monitor resource usage. Keep an eye on resource usage, such as CPU and memory, when working with asynchronous streams. Use performance profiling tools to identify any bottlenecks or areas for optimization. Handle temporary failures gracefully. When dealing with external resources, such as databases or web APIs, implement proper retry and fallback strategies to handle temporary failures and ensure fault tolerance. By applying these best practices, you can maximize the performance and reliability of your asynchronous stream operations in .NET 8. Remember to adapt these guidelines based on your specific use case and requirements. Example applications of asynchronous streams in practice. Asynchronous streams in .NET 8 have proven to be incredibly versatile and valuable in various real-world use cases. Here are a few examples of how asynchronous streams can be applied in practice. When dealing with large volumes of data, asynchronous streams allow for efficient and memory-friendly processing. Rather than loading the entire dataset into memory, you can process it in a streaming fashion, reducing the risk of memory overload and improving performance. Real-time data ingestion. Asynchronous streams are well suited for scenarios involving live data feeds or sensor data. By leveraging asynchronous streams, you can collect and process data in real time, ensuring responsiveness and enabling timely decision-making. Asynchronous streams can be used to achieve parallel processing of data. Resource-intensive operations. Asynchronous streams are ideal for handling resource-intensive operations such as file I/O, network requests, or database queries. With asynchronous streams, you can ensure that these operations do not block the execution of other tasks, resulting in more efficient resource utilization and overall system performance. Avoid blocking operations. Asynchronous streams are designed for non-blocking operations. Avoid using synchronous methods or blocking calls within the stream processing pipeline to maintain responsiveness. Use cancellation tokens. Implement cancellation tokens to gracefully handle situations where the stream processing needs to be stopped or interrupted. This allows for better control and resource management. Optimize memory usage. Be mindful of memory consumption when dealing with large datasets. Consider using techniques like streaming or chunking to process the data in smaller portions, reducing the memory footprint. Handle exceptions gracefully. Implement proper exception handling in your asynchronous stream operations. This includes catching and logging exceptions, as well as considering appropriate retry or fallback strategies. Test for performance. Continuously test and evaluate the performance of your asynchronous stream implementations. Identify any bottlenecks or areas of improvement, and make necessary optimizations. Leverage parallel processing. If your workload allows, consider utilizing parallel processing techniques with async streams to maximize performance and throughput. These are just a few examples of the many possibilities that asynchronous streams offer in real-world scenarios. The flexibility and efficiency of asynchronous streams make them a valuable tool in handling asynchronous data streams effectively. By following these best practices, you can ensure that your asynchronous stream processing in .NET 8 is efficient, reliable, and scalable, delivering optimal results for your application.